This conference will now be recorded.
Hello everyone. So we are starting a new chapter which is some basic principles and techniques of organic chemistry. So this is a completely different branch of chemistry which is organic chemistry. So first we will see as introduction why we need this separate branch of chemistry which is organic chemistry, and here that is today's class we will see first introduction, that is how this organic chemistry this branch arises. Then tetracovalency of carbon, because this chapter is all about carbon compounds. Organic chemistry is based on carbon compounds, so tetracovalency of carbon. Then features of pi bonds, hybridization and shapes of carbon compounds, structural representation of organic compounds, and if time permits, three-dimensional representation of organic molecules. Okay, so as introduction, we can say why we have the separate branch of chemistry which is organic chemistry, and this organic chemistry is based on carbon compounds. But why the element carbon, why not other elements? That is the question. So carbon, this element based on which we have this organic chemistry, it is because of its catenation property. So in the last chapter, that is P block chapter, remember in group 14, the first element is basically carbon, and there we have seen a special property of carbon which is catenation property, and catenation property is possible when there is high bond strength between the same elements, that is bond between same elements. So catenation is maximum for carbon. If you consider the other elements in this group, that is group 14, silicon, germanium, then carbon is that element where maximum catenation property is observed because of its high Cc bond strength. So carbon can form covalent bonds with other carbon atoms, and that is why we can get straight chains. Suppose many carbon atoms, one by one it is forming a chain like this, C, then another carbon, then another carbon. So in this way we can get straight chains because of its high bond strength. We can also get branched chains. Suppose there is one more carbon here or one more carbon here like this. Obviously tetracovalency we have to satisfy, but this type of straight chain, branched chain, and also rings of different types of sizes, that is also possible. So suppose I am drawing a 4 carbon ring. So here it is 2 carbon. To satisfy tetracovalency we have to draw 2 more carbon hydrogen bond, or there may be another carbon, suppose CH3 group, that is methyl group. So in this way ring formation is also possible. Now in this table you will be able to see that if you compare bond strength, then why these Cc bonds, if you look at this value, it is 348 kilojoule per mole. So bond between same element, that is carbon carbon, it is 348 kilojoule per mole. You can also compare with some other elements that are also from second period. I mean to say nitrogen, which is from second period, oxygen, that is from second period. Now look at the value, it is 163 kilojoule per mole, it is 146 kilojoule per mole. And also we have here sulfur bond, which is 266, but carbon carbon bond, it is 348. If you compare same element, that is bond between same elements, okay. Then carbon hydrogen bond, that is also part of organic, that is in organic compounds, carbon hydrogen bonds are also very common, because to satisfy the tetracovalency of carbon we have to place carbon hydrogen bonds, and look at this value, this is also high. Now not just carbon hydrogen or carbon carbon bonds, sometimes some heteroatoms are also present in compounds of carbon, I mean to say organic compounds. So it can also form covalent bonds with atoms of other elements such as hydrogen, that is CH bond that we have just discussed. Then carbon oxygen bond 351, carbon nitrogen bond 293, carbon sulfur, carbon phosphorus, all these bonds are possible. And these type of heteroatoms, that is oxygen, nitrogen, sulfur, phosphorus, that also you will find in organic chemistry. So the study of the structure of these carbon compounds, then properties of these carbon compounds, compositions, reactions, preparation of these carbon compounds. If you combine all this study we do in a different branch of chemistry, which is organic chemistry. So it is all about carbon compounds, and sometimes there is presence of these heteroatoms. Okay. Originally limited to the study of compounds produced by living organisms. So if you consider how what is the origin of these organic compounds, then initially it was thought that only the living organism where the organic compounds are limited, but that is not the case. Now organic chemistry, even it is broadened to human made substances, that is man made substances, and very good example for this is plastic. Okay, so it is not just limited to living organism, that is the naturally biological compounds I'm talking about, but it is also now broadened to some human made substances, that is man made in the laboratory. Fine. So it means that these carbon compounds, they are very versatile in nature, not just natural but also man made. So here you can see all these organic compounds, though all these are related to living organisms such as cell, the basic unit of living things, then deoxyribonucleic acid, DNA, it is a genetic material, then lipids which is found in cell membrane, protein, there is presence of proteins that is just like other biological compounds, and glycogen which is stored in liver. So all these examples that you are seeing all are basically related to living organisms. But as we have seen, it is not just related to living organism, you can also synthesize it, that is man-made. Now here we have some examples. Synthesis, that is, look at this history if we consider of organic compounds. Then synthesis of urea by Wallah, 1828. Then acetic acid, which is having structure like this, CH3COOH, which is done by Kolbe, 1845. And methane, carbon hydrogen compound, by Barthelot, 1856. So synthesis of these are some of the examples, and this basically confirm that organic compounds, it can be synthesized in laboratory, and not just synthesized in laboratory. If we actually see these reactions, they are basically made from inorganic compounds. So it is not that initially it was thought that it is related to living organism and it cannot be prepared by starting from inorganic compounds, but actually that is possible, because that is why it is possible, because these are the proofs that organic compounds can be made from starting from inorganic compounds. Just for example, if we see the acetic acid synthesis by Kolbe, starting from carbon, then we have used inorganic compounds FeH2, then carbon disulfide is produced, then we have again used some non-carbon based compounds, obviously chlorine, CCl4, then in presence of red hot tube there is formation of this type of compounds, though details I am not going, because once we covered its how pi bonds are formed, how that is this type of formula how to write, when we will discuss all these rules, then it will be clear to go into the details. Right now I am not going into the details, I am just trying to show that organic compounds, which is this acetic acid, the final compound, we can prepare it starting from inorganic compounds. Then take the example of urea. Urea is basically having structure like this, NH2, then C double bond O, then again NH2. Now this can be produced starting from ammonium cyanide. Okay, so NH4CNO, which is basically inorganic compound, but from this we can make urea, and that is done by Wallah, 1828. Then formation of CH4, that is methane, that is also possible by the combination of carbon disulfide and H2S, these two together, that is the mixture of these two compounds, mixture of these two inorganic compounds. If we pass it through red hot copper, then there is formation of methane. So all these three reactions are basically the proof that starting from inorganic compounds we can prepare organic compounds. Since then, millions of organic compounds were synthesized and also characterized. Except few inorganic compounds, for example, salt, NaCl, sodium chloride, water. Not just sodium chloride salt, you can also consider any other salt, but inorganic compounds, few inorganic compounds exception, the important aspect of our life, if we see, it is mainly based on organic compounds. It is not that it is wholly based on organic compounds, so that is why the line is starting like that, except few inorganic compounds, because salt, water, these are also very essential for our daily living. So except these few inorganic compounds, important aspect of our life, such as food, medicine, clothing, cosmetic, polymers, etc. All these are basically consisting of compounds of carbon. Okay, so it again proves the importance of organic compounds. So this vast field of organic chemistry, which is dealing with carbon compounds and also its principles, find applications in many industries. And which industries that you can find in these examples? See, food industry, then medicine, pharmacy, cosmetic industry, polymer industry. In all cases, we can see the application of organic chemistry. Next, the growth of electronic theory of covalent bonding. Why covalent bonding? Because when we are talking about carbon compounds, it is based on covalent bonding. Whether you consider carbon-carbon bond or carbon-hydrogen bond, it is not ionic bonding. Okay, no cation or anion. That we see mostly in inorganic compounds, not here. So the growth of electronic theory of covalent bonding further helped in the upgradation of organic chemistry. So as organic chemistry, it is dealing with carbon compounds, and carbon compounds, the bonding is based on covalent bonding, not ionic bonding. So obviously the growth of electronic theory related to this type of bonding, it will help us to upgrade organic chemistry. Fine. So that is all about the introduction part. Next we will see tetracovalency of carbon. Now carbon, as we have seen, it always that is in organic compounds, it is forming mostly CC or CH, and these are basically covalent bond. Now if you expect ionic bonding, then obviously there should be some cation and anion, and in that case it will be either C4 plus or C4 minus, because if we consider its electronic configuration, first of all we will write the electronic configuration in the ground state, obviously for the valence shell, and also in the excited state. Then it will be clear to us how we can get C4 plus or C4 minus, and why basically we are not getting this type of species. Okay, because of the requirement of large amount of energy. So first of all, what is the valency? It is from group 14. Valence electron total number will be the last digit, which is 4, obviously, the last digit of 14. Now carbon, it is also having total 4 valence electrons, and if it is following the general electronic configuration of NH2 NP2, which is for group 14. But for carbon, instead of writing N, we can write 2H2 2P2. Now 2H2 2P2 means it will be like this. Now this is the electronic configuration in ground state when no extra energy is provided. But if it is in excited state, obviously now one electron that will be transferred in, one electron will be transferred in 2p. It will be like this. Now see, you can have now 4 unpaired electrons. Now if we are getting C4 plus species, that means we are removing all these electrons, and to remove all these electrons we have to provide ionization energy 1, ionization energy 2, 3 and 4. Now summation of all these energy values, if you see, it is very high. That means it is highly energy requiring process. So C4 plus formation is not possible. It is true that if you can form C4 plus, then the remaining configuration will be simply 1s2, which is fully filled noble gas configuration of helium. That is obviously stable, but to get the configuration of 1H2, there should not be any electron in 2s and 2p. But that species is difficult to get. That is C4 plus species is difficult to get. Another case if we consider, why not make C4 minus by putting 4 extra electron. Putting 4 extra electron means now from 2s to 2p2, when you add 4 extra electron, it will be converted to 2s to 2p6. But that formation is also not possible because that is also highly energy requiring process. To form C4 minus by electron gain enthalpy, that also should be very high, but that is not here possible. So ultimately what we are seeing, carbon has to form covalent bond only by sharing of this 4 valence electron. So we can get 4 covalent bonds, right? Now when there is sp3 hybridization, that means all these 4 electrons are hybridized. In that case, we will get total 4 sp3, and in each of these sp3, there will be 1 electron like this, and it can share these electrons with 4 other elements. Just take the example of methane. In methane, there is total 4 carbon hydrogen bond. Total 4 carbon hydrogen bond means carbon is using 4 sp3 hybrid orbital for the formation of 4 carbon hydrogen bond. Okay. Now once the hybridization is done, all these orbitals will be having same energy. So ultimately what conclusion we can draw? We cannot have C4 plus, we cannot have C4 minus, as carbon cannot form ionic bond. Because to form ionic bond, there must be cationic species like C4 plus or C4 minus. Complete transfer of electron, that is actually the basis of ionic bond. So it is not possible in this case. So as carbon cannot form ionic bond almost in all compounds of carbon, though exceptions are there where you can get this type of species, but mostly it is forming 4 covalent bonds, and covalent bond means it is sharing of electron. So carbon hydrogen bond, if you consider, there will be 2 electrons, one is coming from carbon, another one is coming from hydrogen, and that is sharing of electrons. Now here one more point we have to remember. Though hybridization we will discuss separately, but still for information I am just saying, suppose instead of sp3 hybridization, if we have sp2 hybridization. Now sp2 hybridization means we are taking 1 2s, obviously 1 2s because there is on just 1 2s only, and instead of taking 3p orbital, we will just take 2. That means this p orbital will remain as pure p orbital. Okay. Now once sp2 hybridization is done, there will be total 3 sp2, and it is easy to understand because when I am saying sp2, that means 1s and 2p. 1s plus 2p, that means p is 2 times. So total 3 hybrid orbital you should get. Total number will be same before and after hybridization. So in S3sp2 there will be 3 electron, and the pure p orbital which is not part of hybridization, this is pure p orbital. Why I am saying pure p? Because it is unhybridized. Here also we have 1 electron. Now remember, when we have pi bond, because 2 to 3 slides after this we are going to discuss features of pi bond, probably in the next slide. Yes. So in the next slide we have to discuss features of pi bond. So just understand this pure p orbital, this electron always will take part in pi bond, not the electrons of hybrid orbital. So these electrons that will always be used for sigma bond formation. Fine. So in this slide we have seen that why there is always sharing of electron. That is why we are having covalent bonds in most of the organic compounds. Next, features of pi bonds. So what are the important characteristics of pi bonds and how it is different from sigma bond? We have to have clear idea about it, because in several compounds of organic compounds you will see there is presence of pi bonds. So we have to know its features. When pi bond is formed, in chemical bonding chapter we have already seen that pi bond is formed by lateral overlap of 2 p orbitals. That is height-wise overlap. When you consider sigma bond, suppose there is one p orbital and another p orbital, and if there is head-on overlap, this is the overlapping part. This is actually sigma bond. But if these two p orbitals, they are sidewise, parallel to each other, lateral overlap. So this type of interaction, that is known as pi bond. Now from this simple picture, it is easy to understand. As it is lateral overlap, obviously the bonding is not so strong as you can expect in case of sigma bond. So that is why sigma bond is always stronger than pi. So pi bond is formed by lateral overlap of two p orbitals, always pure p orbital, oriented mutually parallel to each other but perpendicular to the internuclear axis. That means this is the internuclear axis. If you consider sigma bond, it is just lying on the axis. But for pi bond, it is perpendicular to the internuclear axis, right? So this is the picture for carbon. And as you can see, the green part, that is actually sigma bond. And the blue part, that is actually the pi bond. So this is the interaction. Here you can see pair of electrons. So one electron is coming from the left hand side carbon, another electron coming from right hand side carbon. And in these two electrons are same explanation. So this is sigma bond and this is pi bond. Now as carbon is tetracovalent, and here you can see one pi bond. Just one pi bond you can see here and one sigma bond you are seeing here. So its tetracovalency must be fulfilled. So basically there is two more bonds we should draw like this. So two more bonds will be there. Or it may be that another pi bond is also there. In this case, for simplicity, you are just seeing only one pi bond, which is formed by lateral overlap between two individual p orbital. One is coming from left hand side carbon, another one is from right hand side carbon. Now tetracovalency must be satisfied. Now this second bond, it may be that carbon is forming bond with one hydrogen, or it may be carbon also. For simplicity, I am simply writing H. So if I am writing H like this, that means the actual structure, this is the orbital representation. But if I write it in the bond, then there is a sigma bond between two carbon. There is also a pi bond, and that I am writing using different color. So this is the pi bond in yellow. And rest of the covalency, that is satisfied by hydrogen. Obviously, this is also sigma bond because hydrogen cannot form pi bond. Okay, there is no electron in p orbital. So here you can see the tetracovalency is satisfied, and in this case, the structure, it is basically the structure of ethylene, which we will see after this slide once we finish these features of pi bond section. So here this carbon is basically sp2 hybridized. How we can say so? Because per carbon, just divide it like this because both sides are same. So per carbon there is actually total 3 sp2, and carbon is using its 3 sp2 orbitals for 3 sigma bond. One sigma bond with another carbon, another sigma bond with hydrogen, third sigma bond with another hydrogen. And there is one pure p orbital which is not part of hybridization. That pure p orbital is used for pi bond formation with other carbon. But suppose instead of sp2, if I am having sp hybridization, in that case what will happen? In that case, if it is sp, now there will be total 2 sp because 3 sp is not possible. Now 1 sp will be used for one covalent bond formation, that is one sigma bond. Another sp will be used for another sigma bond, and now we will have pure p orbital, which is total 2. Two pure p orbitals will be there. So we will have 2 pi bonds. So when it is sp hybridized, 2 p orbitals unhybridized. That means 2 pi bonds will be there. And when it is sp2 hybridization, 1 p orbital we have not used for hybridization. So it will be left for pi bond. But when it is sp3 hybridization, suppose carbon is having sp3 hybridization, now there is no pure p orbital, so no pi bond, because you need pure p orbital for pi bond. Okay, and here one thing we have to remember, that pi bond formation is possible which is between two p or p orbitals, only when the sigma bond is already formed. It's not like that you are just having pi bonds and there is no sigma bond. No, it is not like that. First there has to be sigma bond and then only the question of pi bond arises. Now compared to sigma bond, it is obviously weak bond. As we have seen, it is head-on overlap, so interaction is very strong between two orbitals, but in this case it is sidewise, so interaction is not so strong. From this picture also you can understand this part, the overlapping is very intense, but here the overlapping is sidewise, so it is weaker. Pi bond is weaker compared to sigma bond. Fine. Some more points related to these pi bonds we will see. Here we have this plane, as you can see, this light blue colored plane, and this is the interaction zone. Now the two p orbitals, we have drawn it close to each other so that you can actually see the overlapping zone. So this is the overlapping zone, and suppose this is the carbon and there is two more bonds. Now this plane, it is basically perpendicular to the plane of the screen, and these two p orbitals, that is also perpendicular. If you consider this pi bond, that is actually directly lying on the plane, but the two p or p, three-dimensional, if you consider, it is perpendicular to this plane. And once the pi bond is formed, now here the electron density is very high, so you can draw it like this. See, the electron density, now it is above the plane, it is above the plane, and it is below the plane, because these two regions are the regions where maximum pi electron density will be there, not in the middle zone, right? So all the atoms directly attached to carbon atom of the double bond lie in the same plane. So just consider the previous structure where I have added these two carbon hydrogen bond to satisfy the valency. Now these two carbon atoms and all these four hydrogen, they will be in the same plane. That is the plane that you are seeing with sky blue color. But the two p orbitals, that will be perpendicular. Not just carbon hydrogen, I mean to say any other covalent bond that will lie on the plane, but not p orbital. Now this electron charge cloud, this yellow colored electron charge cloud of the pi bond lies above and below the plane of the bonding atoms, and this allows the attack of reagents, allowing pi electrons prone to attack of reagents. Now what type of reagents? Mostly it will be attacked by some electron deficient species, right? Because we have pi cloud above and below. Now suppose I am writing some electron deficient species. Most electron deficient species, it is the term we use is electrophile. Electrophile, in short, we express it like this: E plus. Electrophile means electron deficient species, and which is in search of some electron density. Details of electrophiles will be discussed later in this chapter, but right now just see, E plus means electron deficient species, and it will be attacked by this pi electron density. The sign of arrow that I am using, it is always from the electron dense region. It is electron dense region, right? And this region is electron deficient region. So the sign of arrow, that is the direction of arrow, it is always from the dense region towards the deficient region. So that is why the direction is like this. So there is a tendency to attack by electron deficient species above and below. The carbon forms relatively short bonds. It means when you consider two carbon, when they are coming close to each other, this carbon-carbon sigma bond, that is actually very short distance, because carbon is from second period, 2p orbital. So they are very short, having short distance, and that is why this type of overlapping, that will be easier. Suppose the carbon, the distance is very far from each other. If they are not from second period, then interaction will be very weak. The more closer they are, better is the interaction. So because of this relatively short bond between two carbon-carbon, that is the sigma bond is short, that lateral, it enables lateral overlap of this pure p orbital or unhybridized p orbitals of carbon to form these pi bonds easily. And one more point, when you are having multiple bond, Suppose CC single bond means what? There is only sigma bond. But when there is carbon-carbon multiple bond, suppose CC double bond or triple bond, these are the only two possibilities. So in this case, when there is double bond, it is basically 1 sigma 1 pi. And here the hybridization of carbon is sp2. And when there is 3 bonds, then the first bond is sigma, this is pi, this is also pi. And here hybridization is sp. See, it is easy to remember. Why? Because when there is 1 pi bond, here we have 2 pi bond. 2 pi bond means 2 pure P. 1 pi bond means 1 pure P left for pi bond. So it is easy to remember in this way. There are 1 and 2 pi bonds in double bond and triple bonds of carbon respectively. So in this case you have 1 pi bond. Second case, that is sp hybridization, you have 2 pi bonds. And when it is sp3 hybridization, there is no pi bonds because you do not have any unhybridized p orbital. Okay. So these are the features of pi bonds. Next topic is hybridization and shape of carbon compounds. So how the hybridization is occurring, that we have already seen. And in this picture, already the excited state you can see, because we have already unpaired the electron that is present in 2s. 1s is undisturbed. You don't have to consider it. Just consider in this part. When it is sp3 hybridization, the 2s and all these will be mixed up and you will get total 4 sp3. When it is sp2, then 1s and 2p mixed up, this is pure. We will get total 3 sp2, and for sp we will get total 2 sp. So this is the mixed up region, these two are pure. So in this case there will be 2 pi bonds, in this case there will be 1 pi bond, here 0 pi bond. Now the very good example and simple example for these 3 hybridization of carbon compounds is methane. So this is for sp3. That is the example of sp3 hybridization. Ethylene. Actually ethylene you have already seen the structure. Remember the previous structure that we have seen for ethylene. So in this case you have 1 sigma bond, 1 pi, and these two carbon, both the carbons are sp2 hybridized. And ethine, which is also known as acetylene, this is basically the example of sp hybridization. Now how I will draw it? It is simple. If you know, that is, you have properly understood this structure, now what I will do extra, one more bond I will draw. So in the previous structure you just have 2 bonds between 2 carbons, but now I have drawn 3. And to satisfy valency we just need 1 extra covalent bond. So in this case we have 1 sigma, 2 pi. So these are the good example for these 3 different types of hybridization, and it is the simplest example that is possible. Though that is more, as we proceed in this chapter you will see more complex structure that where you will find these 3 hybridization. But right now, as we have just started to understand what is sp3, sp2, sp hybridizations are, so these 3 examples are good examples. And methane is like this. So when there is sp3 hybridization, all these carbon hydrogen, that is bond angles, it is same as we know in tetrahedral environment, and that angle is 109 degree 28 minute. And in this case, all these, that is in the second case, C2H4 ethylene, all these 4 hydrogen and the 2 carbon, we know they are in the same plane. And in the last case, this is actually see linear structure, right? And here we will have 2 pi bonds, and the 2 pi bonds that will be perpendicular to each other. Details of the orbital representation of these 3 molecules we will see in the next slide. So the first example, methane. The hybridization is sp3. So as you can see, carbon, the central atom in CH4, carbon is using its 4 sp3 hybrid orbitals for bond formation with 4 hydrogen atoms. And hydrogen will use its 1s orbital, that is fine. So this is the overlap between 1s of hydrogen and sp3 hybrid orbital of carbon. And the angle is 109 degree, 28 minutes. All these angles are same. The next structure is ethylene, which is example of sp2. So when it is ethylene, that is C2H4, now see this is the structure, and here this angle is also this angle, HCC angle or HCH angle. All these angles are 120 degree. That we always get from sp2. Now come to this orbital representation. There is one sigma bond, there is one pi bond. So this is the sigma bond head-on overlap. This is the pi bond which is lateral overlap. These two are the carbon-hydrogen bond. So carbon is using 3 sp2 orbital. One it is using for CC bond formation. Another sp2 carbon is using for carbon-hydrogen bond formation. The third sp2 is also used for carbon-hydrogen. And the pure p orbital, the one electron that is remaining in pure p orbital, that electron is used for pi bond formation. Okay. And here, in this way, you can understand how the 4 valence electrons are utilized. One sigma, one pi between two carbon. The next example, which is for sp hybridization, that is ethyne. It is also known as acetylene, which is the common name, but IUPAC we use ethyne C2H2. So see, as I have said, this is linear, so this angle is 180 degree. Now in this case, carbon will have 2 sp hybrid orbital and 2 pure p orbital. So carbon is using this electron is coming from hydrogen and another electron is coming from carbon. So carbon is using one sp for bond formation with hydrogen, another sp carbon is using for bond formation with another carbon, and these two are pure p orbital. This is pure, this is also pure. So if it is that is if you consider this pi bond in this plane, then I am using another color to show another pi bond. So this pi bond, it is completely, if I color this plane, that is green color, it will be the plane where this pi bond is present and it is perpendicular to the internuclear axis. Similarly, if you consider this yellow plane and this green plane, these two are also perpendicular to each other, right? So if I am drawing with different color, so this is one pi bond, and then another color I am using, and you can see this maroon one is perpendicular to the green one. So two pi bonds, fine. So here we have two pi bonds and one sigma bond. So pi is formed between two pure p and sigma is formed between sp of one carbon, sp of another carbon. And here hydrogen is using its 1s orbital. So this is the hybridization and shape of carbon compounds. This is planar because if you join all these atoms, you will get a planar structure. And individually, if you consider carbon, all these three bonds are in the same plane and these angles are 120 degree. Whether you consider HCH angle or HCC angle, it is 120 degree. And in case of ethyne or acetylene, it is always this is 180 degree and it is linear. So sp3, it is tetrahedral. The next one sp2, it is planar, and this one, that is the last one, sp hybridization, this is linear. Okay. Next we will see structural representation of organic molecules. So when we are saying structural representation, there are actually different ways by which we can do this structural representation. Okay. So molecular formula of a compound, we know this is the simplest, least informative representation, because when you simply write the formula, basically you cannot understand the details of bonding. So that is why it is mentioned as least informative. You just get to know what is the total number of elements, what are the different number of elements. So this simplest least informative representation showing the number of atoms of different elements, suppose 2 carbon, 3 hydrogen, like this, present only. Now for organic compounds, there are actually different ways you can represent the molecule. So there are some representation where you can get some more information, though it is mentioned as least informative representation. But depending on which of these you are actually using, sometimes you can get least information, sometimes you can get more information. So we will see all of this. But remember, the first one we will not go into the details, because this Lewis or dot structure mainly used for inorganic compounds, where you will be able to see all the bonding electrons, all the non-bonding electrons with dot sign, right? Just take the example of hydrogen HCl. So here these 2 electrons, one is coming from hydrogen, another one is coming from chlorine, and chlorine is also having 3 lone pairs, so we simply draw it like this. But when it is organic compounds, Lewis dot structure actually we do not use. So mainly we will focus on these 3. Now the first one, that is complete structure or dash structure. So this structure is basically directly you will be able to understand all the bonds that is present. So that is why it is complete structure. So this is the most informative structure among these 3. So in this complete structure, it is obtained by representing a pair of electron in a covalent bond. Because see, when I have drawn HCl bond, what we draw? We draw a bond like this. Though in Lewis we write it like this. We do not write a dash. We draw it like H dot dot then Cl. But when it is organic compounds, we represent it with a dash or simply a line, small line. So when this is single line, it represents single covalent bond. Just take the example of methane, where you have only single bond. So in case of methane, we have 4 carbon hydrogen bond. So here we have single bond. But suppose if it is double bond, which is basically consists of 1 sigma 1 pi. Just take the example of ethylene. So in this case, what we have seen, there is double bond. So we are now representing it with 2 parallel lines. And if it is triple line, that means it is triple bond. So that also we have seen like this. In case of ethylene, ethyl. Now it is 1 sigma 2 pi. Now lone pair of electrons, if any heteroatoms present. So in these 3, you do not have any heteroatom, but suppose heteroatoms are present. For example, oxygen is present, carbon-oxygen bond is present. And when there is carbon-oxygen bond, suppose there is carbon-oxygen bond and then there is a hydrogen. Now oxygen, it is bivalent, right? It will use 2 of its electrons. But rest of the 4 electrons, that will remain as lone pair. Now you can either represent it, or if you do not, that doesn't matter. So it may be shown, it may not be shown. Now here we will see some examples of complete structure. Now one example we'll see, which is for 1-chloropropane. Though right now, as we have not yet started, that is, we have not completed the IUPAC nomenclature. So if I say that 1-chloropropane and then I draw, it will be difficult to make you understand. But simply as I have to use some name, so that is why I am using it 1-chloropropane. So 1-chloropropane means the structure is like this. Propane means there will be total 3 carbon. Though details of IUPAC rules that will be discussed separately, but just for the sake of drawing this structure, I am just using the name. So 1-chloropropane, see all the bonds I am writing in detail. Propane means total 3 carbon. and there is one carbon-chlorine bond. Now, for this left-hand side carbon, I am numbering it 1, 2, 3. For the 3 number carbon, we have already seen it is satisfied, tetracovalency is satisfied. But for 2 carbon, we have to satisfy it. So we are placing 2 more hydrogen. And here also we have to satisfy it. So we are placing again 2 more hydrogen. Now chlorine, it is by a single bond will be there. If you want, you can put lone pairs. If you do not write, that is also fine. Most of the time, the lone pairs are not drawn to make it simple. So this is the structure where we are seeing only single bond, but we can also have one more example where you will be able to see pi bonds. So suppose the next molecule H carbon, then another carbon hydrogen. Now there is a double bond. Then again there is a single bond, and there will be one more hydrogen because to satisfy the valency of it. Now I will draw a 3 carbon. So see, in this case we have some multiple bonds, 2 bonds or 3 bonds, but all the bonds are drawn in detail. And the third example I'm going to give, that will be a cyclic compound, 5-membered carbon, 5-membered ring basically, and all these 5 atoms are carbon. Now there will be, suppose, one bromine substituent, and here one methyl substituent, that is CH3. But for other carbons, we have to satisfy the valency. So we have to draw carbon hydrogen bonds. Okay. Now the same 3 molecules I will also draw for condensed structure and bond line structure, so that you will be able to differentiate the difference between complete structure or dash structure and condensed structure or bond line structure. What is the difference? So to understand that, sorry, there will be one more hydrogen. To understand the difference, we should use the same example. So the same molecules I will also draw for condensed structure and bond line structure. So next, condensed structure. So as the name suggests, condensed. Now we will not draw the that is all the bonds will not be drawn elaborately. It will be drawn as condensed way. So what we will do, structural formula can be further condensed by enclosing the repetitive structural unit. So suppose there is 2 CH2 group, 1 by 1. So we can write it CH2 whole 2. So repetitive structural unit we can put in bracket and placing an integer as a subscript, which will indicate the number of times that that particular structural unit is repeated. So now same examples I will write. Remember 1 chloropropane. So now 1 chloropropane will be written like this: CH3, then CH2, it will be repeated 2 times, and then there is Cl. So I have not used any dash. Remember the difference with the previous structure, there is fully, we have drawn all the carbon hydrogen bond, carbon chlorine bond, but now the CH2 unit, which is basically repeated. Suppose if I am not drawing CH2 whole 2, then it will be like this. I am not using any dash line. But to make it simple, now it is CH2 whole 2. So in this case, you can draw the full structure. But suppose instead of 2, if there is 6 CH2 units or 7 CH2 units, it is very difficult to write all these CH2 like this. That is 6 CH2. If you write, it will take a lot of time. So no need to do that. What you will do, simply put a subscript for the repeating part. Now for the next example, where we have seen some double bonds or triple bonds, in the condensed way, when we will draw it, now for double bonds you have to draw with dash, because there is no other way. How we will make understand that there is a double bond? If you simply, so let me first write the condensed structure. It is like this. But suppose instead of writing, you are writing like this: CH2, then CH, then CCH. It is really difficult to understand whether there is any multiple bonds present or not. So when there is only single bond, you don't have to draw the dash. Just the first example. This is the example number 1. In the first example, there is no multiple bond, so you don't have to put any dash. But when there is multiple bond, in the second example, now you have to draw it. Don't draw it like this. This is the ideal way to draw it. H2C double bond CH, then C triple bond CH. And if you observe carefully, valency for carbon, which is 4, that is satisfied. Now the last example we have seen, which is basically cyclic structure, ring structure. Now how we will draw it? H2C CHBr. Now as it is ring compound, now you have to put these lines. We do not have any other option. But see, this CH2, we have not written the full bonds. We have simply writing it as CH2. But this area, that part you have to use bond. Because if you do not use that straight line, how we will draw the ring? So that is why you have to do it. But see how I am writing the CH3, it is just as if a group. Then one more CH2. So for these parts, okay, let me use separate color. So for these parts, we have to draw a line. We don't have any other option. But see, these groups are written as CH2. It is not in the previous case, we have written it like this. But here we are simply writing as CH2. Okay. If the ring size is very large, then also this type of subscript you can use. Suppose the ring size is 10. So what you can do, write some CH2. And in some cases, you can put CH2 whole N so that you don't have to draw all the CH2. Okay, that depends. That only for large ring size. Now the last one, which is bond line structure. So in bond line structure, it will now, if you see the structure, it looks very simple, but yet you get all the understanding of all the bonds present. Now this is the most simple, short. It is actually less time consuming. So that is why mostly we draw this type of bond line structure for organic molecules, where we do not use any details of the atom. So this is the most simple, short, less time consuming and convenient also, representing organic molecules. Now in this structure, we do not mention the carbon and hydrogen atoms that are not shown. Only simply lines are drawn for the representation of carbon-carbon bonds. So suppose I am writing a straight line. What it means? It means both the terminal position there is carbon, and to satisfy it there is actually 3H. So this line that I am drawing here, it basically means this molecule. Isn't it simple? So carbon hydrogens are not shown, and carbon-carbon bonds are drawn as zigzag fashion. So here we have only one carbon-carbon bond, but suppose if it is more than one carbon, now we have to draw it with zigzag way. So the first example that we have already used for condensed for the previous two types, that is 1-chloropropane. Now I will draw it in zigzag way. In the last part there is chlorine, but rest of the portions I will not draw carbon or hydrogen. So only the heteroatoms we are writing. It may be any halogen, chlorine, bromine, iodine, oxygen, nitrogen, sulfur, phosphorus. Mostly these heteroatoms are observed. But see, I have not drawn carbon or hydrogen. So that is why it is less time consuming. Now, a single bond is represented by a single line. If it is double bond, it will be represented by two lines. Now, the second example, remember, in that case, there is double bonds. There is presence of double bonds. So how we will write it? This is double bond. Then there will be a single bond. And after the single bond, there is a triple bond also. Now, don't draw the triple bond like this. Don't use again zigzag, because carbon-carbon, when it is in triple bond, they are always linear. Remember the structure of ethine. This angle is always 180 degree. When it is sp2, it is always 120. So that is why try to maintain this as 120 degree and do not draw it like this. So I will erase it and draw it again like this. So now it is 180 degree. So it should be drawn like this. Now I will remove this value so that you can see the structure properly. It is. So I have not drawn any carbon or hydrogen, and in this structure there is no heteroatom. So each carbon on the line or intersection is attached to necessary number of hydrogen. So see, this zigzag part here there is actually 2 hydrogen. Though we have not drawn it, just to make you understand, I am drawing it. And the terminal position, there is actually 3 hydrogen. That is, it means there is 3 hydrogen. Obviously, we will not draw it. So the terminal point denotes a CH3 group and the junction of 2 lines. So this is the junction of 2 lines. There will be presence of CH2. Now this is also junction, but this is not CH2. There is simply 1 hydrogen because we have already multiple bonds. Now remember the ring structure, 5-membered. We do not draw any carbon or hydrogen. So simply it is a 5-membered ring. And there is a bromine heteroatom that also we have to draw, and the methyl group that we have to draw. There is no other. You can also draw it like this. Don't, even if you do not write methyl group, you can draw it like this. But even if you do not draw it, that is by default, it means there is a CH3 group. So the same 3 molecules we have drawn them in bond line, in condensed, and also in complete structure. Now all these examples together, if you see, first the molecular formula, these are basically IUPAC names. Right now you will not be able to understand why these IUPAC names are written in this particular ways, because there are some rules that will be discussed separately. But look at the first type of structure. This is complete, where you can see all the details of bonds. But complete structure we write hardly because it takes a lot of time. These are simple molecules, you can draw it. But when the structure will be more complex, it is mostly the bond line structure that we draw. So the same molecule means it is 1 chloropropane. But first you are seeing the complete structure. Next you are seeing the condensed structure, and third, that is the bond line structure. Then for the second example, remember this angle, it will always be 120 degree, and there is imaginary hydrogen. Basically I'm saying imaginary because we are not supposed to write hydrogen in bond line structure. So these angles are always 120 degree because it is sp2, and this angle is 180 degree. So never draw it like this because it is zigzag. No, it is not ideal way to draw it because you have to maintain the angle. And then the last one, where it is ring structure. Okay, so here all the details of bonds. Then in the second one, though these bonds you have to draw, there is no other way because ultimately we have to understand this is ring structure. But these are drawn as condensed way, not the full structure. Actually, this should also be written like this. For space problem, it is simply written as CH3, but full structure for complete. So these are the difference between complete structure, condensed structure, and bond line structure. From now on, mostly we will use the bond line structure because this is the less time taking process. If you draw complete structure, this will take a lot of time. Okay. So mostly condensed structure or bond line structure, these two are used. So we'll end the session here. Next, you will see the classification, that is from based on structure, we see the classification. So we are ending the session here. Thank you for listening.